Okay, so if no one has any questions, then the first thing I want to do is I actually want to share my screen because I want to show you like a sheet that I'm going to be referencing and that you will probably want to reference when you are doing these problems for all the stuff kind of in chapter 5. And so we're not going to reference it a huge amount today, but we will actually use it a ton next class. The next couple classes, I should say. Okay, so let me share my screen here. Okay, let me pull up the chat so that you guys have questions. Okay, so on Canvas, right, this is our course, and Canvas is having a little bit of issues, which is why some of those buttons, let me see if I reload it. Maybe it'll reload my buttons here. Yeah, there we go. Okay, so we had gotten an email that Canvas was having some issues. So if you, yeah, like it's missing it's missing my handout page, right? Because it's still not, let me see. There we go. Okay. So there's a button that says handouts, right? Usually on Canvas, but it's having a little bit of issues here today. But if you clicked on the handouts button, you would come to the handouts page here. And this right here, this Trig Identities sheet. So this is what we're going to be using for the next couple classes. So on here, right? So it's going to preview it for me. So you do not have to print this out. However, it is going to be, if you happen to have access to a printer, it might be helpful to have this printed out in front of you for the next couple classes, okay? Today, we're only going to be dealing with these things in the box, and so I'll write them down on the iPad, like on the screen when we do them. But in the starting like next class, I'm not gonna. I will write down the ones we're using, but like I'm not gonna write all of these down. I might kind of pull up some of them and stick them into our thing. And so if you go through here and you can like scroll down and you can see like this goes longer. Right, so we're going to go through basically all these identities. So the next couple sections in chapter 5 are all about working with these identities. Today, we're just going to be working with these identities that are in the box. So the quotient and reciprocal identities and the Pythagorean identities. So these are going to be the main ones that we use today. And so we're going to go through these here in a couple of minutes. So any questions so far? Let me record. So his first couple identities from that sheet that was on the stuff. And this is section 5.1, which is fundamental. Fundamental trig identities. I do not know why my pen doesn't want to. What's going on here? Okay, so those identities that were on, oh yeah, no, I started it. Okay, so but thank you. Those identities that were on the sheet, the ones I said that we're going to need to remember, or the ones you need to know for calculus, are the quotient and the reciprocal. So the quotient and the reciprocal. And so the reciprocal ones first. So the following are the reciprocal ones. So remember when we were talking about like when we found sine and cosine and tangent, we found cosecant and secant and cotangent by flipping those over. So that's what the reciprocal identities say. So they basically say that the cosecant of theta is 1 over the sine of theta. They say that the secant of theta is 1 over the cosine of theta. That the cotangent of theta is 1 over tangent theta. And those are kind of the three that we have been using, right? We would find sine, cosine, tangent, and flip them over to get the cosecant, secant, cotangent. But remember, the flipping over works both ways. So, like, if you took tangent and you flipped it over to get cotangent, you could flip it back over again to get back to tangent again. So we can also say that the tangent of theta is equal to 1 over the cotangent of theta. We can also say that the sine of theta is 1 over the cosecant of theta, and that the cosine of theta is 1 over the secant of theta. And then, so that's kind of that's like the reciprocal identities. There's the quotient identities, which are saying that the tangent of theta is equal to sine theta over cosine theta, right? And so the reason why that is because remember, tangent is y over x, and y is the sine and x is the cosine. And then same thing, the cotangent of theta is the cosine of theta over the sine of theta. And then there's the Pythagorean identities. And the Pythagorean identities, the most common one says sine squared theta plus cosine squared theta equals 1. And then there's two others. So let's talk about the Pythagorean identities, because the quotient and the reciprocal identities are just kind of based off of the definitions of sine and cosine and secant and cosecant and cotangent and all that. But where the Pythagorean identities come from is, so if I have some point on the unit circle, right? So here's the point x comma y. And we're on the unit circle, which means the hypotenuse is 1, right? So if you think about this triangle, this distance down here, let me make it red here. This distance here is the x, and this distance here going up, that's the y. So the reason it's called the Pythagorean identity is because it really comes from the Pythagorean triangle. Or Pythagorean theorem that says a squared plus b squared equals c squared. Or in our case, in terms of this triangle I have here, it's saying that x squared plus y squared equals 1 squared, right? So if I plug into the Pythagorean theorem, I get a squared plus b squared equals c squared. So in our case, x squared plus y squared equals 1 squared. And then if we think of this angle here as theta, remember x is the same as sine theta. So the sine of theta squared, y is the same as cosine, plus the cosine of theta squared, equals the hypotenuse squared, so equals 1 squared. And so writing sine with the little 2, that's just a shortcut. Yeah, it works based off of the unit circle, but it will work for any angle, the sine of that value. Because you can think about it, if I had a bigger triangle, it would be a similar triangle, and so the proportions actually have to work out to be the exact same thing. So it technically works for bigger circles, but we're basing it off of the unit circle. Does that make sense? No problem. So here, when we write sine with a little 2, that is shortcut notation for saying sine of theta squared, right? And then when we write cosine with a little 2, again, that's shortcut notation for saying cosine squared, and then 1 squared is just 1. So that's where I get this first Pythagorean identity from. So sine squared plus cosine squared equals 1. So it comes off of the unit circle by drawing a triangle, and then working on the unit circle to get that relationship, and then the fact that we know that x is represented by the sine function and y is represented by the cosine function. Questions on where that first one comes from? Okay, and then if anybody remembers from looking at when I flashed up that big sheet, there were actually 3 under the Pythagorean identities, okay? And so I only ever memorized the sine squared plus cosine squared equals 1, and then I remember how I can get the other ones. So if you start with sine squared theta plus cosine squared theta equals 1, and we divide everything by sine squared. So I divide this part by sine squared theta, this by sine squared theta, and this by sine squared theta. So sine squared theta over sine squared theta is 1. So this is going to be 1. Plus, now if I look over here, cosine over sine, we said was cotangent. So this is going to be 1 plus cotangent squared theta. And if we look here, 1 over sine is cosecant. So 1 over sine squared would be cosecant squared theta. So that's another way of writing a Pythagorean identity. The second one is that 1 plus cotangent squared theta equals cosecant squared theta. So as long as you know sine squared plus cosine squared equals 1, you can get the other one. And we can even get the third one. The third one is done the exact same way, but this time, I think I can fit it in here. I'm going to kind of box this off so I don't run into it. If I start this time with sine squared theta plus cosine squared theta equals 1, and this time I divide everything by cosine squared theta. So sine squared over cosine squared is tangent squared theta. So we get the tangent squared theta plus 1 equals 1 over cosine squared theta is secant squared theta. So tangent squared theta plus 1 equals secant squared theta. Questions? Okay. So that's kind of where all the ones that we're going to use today are going to come into play. So what we're going to do today is we're going to actually take these identities and we are going to use them to help us simplify some things and then also to help us prove some things. But those are the identities we're going to use. And we're so those 3. For example, simplify. So my first one is the cosecant of x times the cotangent of x. So in this case, right, basically I want to see if there's something that I can kind of like somehow make this simpler. It looks pretty simple, but it's possible that this might actually even turn into an even more simple trig function. So one of the things I can do is on the last slide, right, we had stuff for what the cosecant of x was. So remember, cosecant of x is 1 over sine x. And the cotangent of x is the same as... Oh, I wrote this wrong. Whoops. Sorry. This is not supposed to be cotangent. Well, I guess it's fine. We could do it as cotangent of x and see what happens. Okay, so, no, cotangent's just going to make it ugly. I meant to write cosine of x. It's just been one of those days, right? Okay, so I've got the cosecant of x which I can't, which the cosecant of x I can write as 1 over sine x. I have the cosine of x, and there's nothing really for me to do with the cosine of x, so I'm going to leave it as cosine of x. But the thing I can do here is I can think of this as the cosine of x over 1. And so now I have two fractions that I could multiply together. So if I multiply these together, I end up with cosine x on the top and sine x on the bottom. And so when I do that, cosine x over sine x is just actually equal to the cotangent of x. And so all that I've done is I've used, the first thing I did was I used a reciprocal identity, and then the second thing I did was I used the quotient identity. Questions? So I should say that section 5.1 here is a lot about getting us used to the idea of just like working with these identities. No. Okay, so let's try another one here. And this time I'll actually write out when I'm doing it, like what I'm using in each step. So cosecant squared x times the tangent squared of x times the secant of x. So I could rewrite each of those. So I could rewrite what the cosecant is, I could rewrite what the tangent squared is, and I could rewrite what the secant is, because I could rewrite them all in terms of sines and cosines. So the cosecant is the same as 1 over sine, so the cosecant squared would be the same as 1 over sine squared of x. The tangent squared x is the same as the sine squared x over the cosine squared x. And the secant is the same as 1 over cosine squared x. Oops, not cosine squared, just cosine, right? Because we don't have a... So 1 over cosine x. Okay, so does anybody see anything that I could possibly do with that, right? So all I've done right this second is I used the quotient and reciprocal identities to rewrite. So can you see any algebra? Okay, yeah. So, right, exactly. So you could, so the sine squareds, because I happen to have a sine squared in the top and a sine squared in the bottom, the sine squareds will cancel each other out, right? So these cancel each other out. And then if you think about multiplying across the top, I have 1 times 1 times 1, right? Because sine squared went into itself 1, sine squared went into itself 1. So on the top, 1 times 1 times 1 is 1. And on the bottom, I have a cosine squared times another cosine. So just like if I have x squared times x, that would give me x cubed. Cosine squared times cosine would give me cosine cubed. So cosine cubed x. And all I did in this step was some algebra. Right? I just used what algebra is. And then I can rewrite 1 over cosine of x is secant, so 1 over cosine cubed of x would just be secant cubed x. And so basically I've used that reciprocal identity again. Reciprocal identity. Questions? No. All right. Should we look at another one? How come on the problem A we left cosine x over 1? Okay, so in general, one of kind of like the main strategies of these problems is when in doubt, try to change everything to cosines and sines. So in part A, cosine x was already as a cosine, so that's why I left it and I didn't do anything with it. Yeah, I could have rewritten it as 1 over secant, but we tend to try to change everything to sines and cosines to see if anything will cancel out or if we can multiply and make anything a little better. Does that kind of help? No problem. Other questions? No. Yeah, I'm going to do more. Yep. I got a whole bunch. So this is C. Sine squared x plus 1 over cosine squared x plus 1. Okay. So in this problem, right, everything's kind of already in terms of sines and cosines, but I have two pieces, right? I have that first fraction here, and then I have this plus 1. And so if you have two separate pieces, one of the things sometimes you want to do is you want to put it together into one piece, because we're trying to see if we can get this to simplify down into like a single trig function, or maybe just one trig function plus another trig function. So the first thing I want to do is I want to add these two things together. So what, in general, if you're trying to add a fraction to something else, what do you have to do to add a fraction? When you're adding with fractions, what do you have to have? Yeah, you have to have a common denominator. So we're going to have the same thing. So our first fraction, the bottom is cosine squared x. And remember, we can think of the second one, it's really a fraction too. It's 1 over 1, but I want the denominator now to be cosine squared x. So I'm going to have to multiply the bottom by cosine squared x, which means I'm also going to have to multiply the top by cosine squared x. So basically what I did was I multiplied the bottom here by cosine, or the top here by cosine squared x, and the bottom also by cosine squared x. So I multiplied by the same thing on the top and the bottom. So I didn't change my fraction, it just looks different now. It's like it put on a Halloween costume. That's kind of what I like to say, right? It didn't change who it is, but it just looks a lot different. Questions about what I've done so far? Okay, and all I've done here is a little bit of algebra, right? So I haven't done any like identities or anything like that. Just use some algebra. And so now if I have the same denominator, I could add my two fractions together. So when I add them together, the bottom is still going to be cosine squared x. But on the top, we're now going to have sine squared x plus 1 plus cosine squared x. So again, all I've still done is algebra. Right? So I took my original problem, I made it have the same denominator, I added my two fractions together. Questions? Okay, so I'm just going to rewrite stuff a little bit. So I'm going to rearrange the terms on the top. It's addition, so the order that I write them in does not matter. So I'm going to group the sine squared x and the cosine squared x together. So sine squared x plus cosine squared x plus 1 all over cosine squared x. So again, all I've done is some algebra. Yeah, so yes. So good question. So cosine squared x means, you could think of it two ways. You could either think of it as the whole entire cosine x squared, which that means cosine x times cosine x. So the reason that we write it this way, right, rather than writing it this way, is because this, if I write it this way, I have to put parentheses. And I kind of like to say sometimes mathematicians were lazy people. And so if I write it this way, I have to put the parentheses in. But here, if I put the 2 between the cosine and the x, I don't have to write the parentheses. So it saves me like 2 parentheses of writing. And so it's a shortcut notation that basically mathematicians use on trig functions. So if you have a power between the trig function and the x, it's really saying it's that whole entire trig function raised to that power. Does that help? No problem. Other questions? No. Okay. So I rewrote this here. I happen to rewrite this because now I have a sine squared x plus a cosine squared x. Does anybody remember what the Pythagorean identity tells us that's equal to? Yeah, 1. So this is equal to 1 plus 1 over cosine squared x. And that's because I used the Pythagorean identity. And now I can simplify. 1 plus 1 is just 2. So this is 2 over cosine squared x. So again, I just did some algebra. And then I can really think of this as 2 times 1 over cosine squared x. And again, that's just algebra, right? You can kind of separate a fraction like that anytime that you want. And the reason that's helpful is because 1 over cosine is secant, so 1 over cosine squared is going to be secant squared. So this is 2 secant squared x, and that's because we use the reciprocal identity. So I started with this ugly part that was sine squared x plus 1 over cosine squared x, and then that whole entire quantity plus 1. And really, it's the same as 2 secant squared x. So 2 secant squared x is a little bit nicer looking. So that's one of the reasons why I would do this. Questions?
What happened to the sine squared x? I think I missed something.
Whoops, wait a minute. I just had my sound turned down. Say that one more time.
What happened to the sine squared of x? Like, how did it turn into 1 plus 1?
Okay, so this whole part here is from, so yeah, so this is the unfortunate thing of, right, that we're in this online environment, because usually I pass out that, like, trig identity sheet so you have it in front of you. But one of those identities, the Pythagorean identity, tells us that sine squared, I think the way it's written is sine squared theta plus cosine squared theta equals 1. And so instead of thetas, we have x's. So sine squared x plus cosine squared x is always going to be equal to 1. So basically what I circled here in pink, I'm saying that this sine squared plus cosine squared, this is equal to 1. So that's how I got to 1 plus 1.
Oh, okay.
Does that make sense?
Yeah, thank you.
No problem. Other questions? No. Okay. So I have one more of these that we're going to try. And then we're going to do something else, which is still going to be doing this type of stuff. So we're going to get even more practice with it. Okay. So D tangent squared x plus 2 tangent x plus 1 all over sine x tangent x plus sine x. So, this one's kind of ugly looking, right? You could change all the tangents into sine over cosine, which might help us out a little bit, but it's not going to help us out as much as we would like. And it's just going to make, now I have one fraction, and within the one fraction, I have a bunch of other little fractions. So another trick that sometimes comes in these is you can actually factor them. So let's look at the bottom first. So if I look in the bottom, I have two pieces. I have the sine x times tangent x, and then I have the sine x. This is my second piece, right? So my first piece is the sine x tangent x. My second piece is just the sine x. Do those two pieces have anything in common? Yeah, they have a sine x in common. So what that means is I could factor the sine x out. It's just like if you happen to have, say, 2y plus 2, right? I could factor the 2 out of that. If I factored the 2 out of this, I'd have 2 times the quantity y plus 1, right? Because if I distributed that 2, I'd get the 2y. 2 times 1 would give me the 2. Same thing here. The thing I'm going to pull out isn't a 2. It happens to be a sine x. So if on the bottom, if I factor out a sine x, I'm going to have sine x times the first piece, I'm going to be left with a tangent x. And then in the second piece, I took the whole entire sine x out. But when you factor something out, you have to leave a placeholder if you take the whole entire thing out. And that placeholder is always a 1. So the bottom factors into sine x times the quantity tangent x plus 1. And if you're like, I don't like that plus 1, think about it. If I redistribute this, sine x times tangent x would give me this first part, sine x times tangent x. Sine x times 1 would give me the second part, sine x. Questions about the bottom? No. Okay, we're going to factor the top as well. Now, the top's not quite as easy, right? The top shows just you have like tangent squared x plus 2 tangent x plus 1. So it's not like there's something in common between all the pieces that I can pull out. So on the top, you want to think about it as I have something squared, so think about y squared, plus 2 times something, so 2y plus 1. So this is now like a problem we would have seen in Math 96 or Math 126. So how do I factor y squared plus 2y plus 1? I know you guys know how to do this. It's the same as if it was like x squared plus 2x plus 1. Yeah, how do you factor it? It would factor into what? So this is going to factor into something times something. Yeah, not quite. It's not y minus 1 times y plus 1. Y minus 1 times y plus 1 would give me y squared minus 1. But you're on the right track. So I have a y squared, right? So first off, this is going to get a y and this is going to get a y. And then I'm looking for two numbers that when I multiply them together give me a 1, but when I add them together give me a 2. So can you think of two numbers that when you multiply, one number times the next number gives you a 1, right? And you add them gives you a 2. So, right, it's going to be a plus 1 plus 1. So this is going to be y plus 1 times y plus 1. Or another way of saying, so if you wanted to, you could rewrite it as y plus 1 quantity squared. That's another way of saying it, but we're just going to leave it as y plus 1 times y plus 1. So the thing is we don't have a y, right? What do I have instead of a y in my original problem? Yeah, I have a tangent. So this is going to factor into the tangent of x plus 1 times the tangent of x plus 1. So anytime you're trying to factor these things that have tangents and stuff on it, the first thing you want to do is you want to think about it in terms of just like if it was a y, right? So take out the trig part first, and if you have trouble kind of looking at something and factoring it, take the trig part out and think of it like just an algebraic expression, like you would have done in Math 96 or 126. Okay, so now I've got it factored, right? So again, the only thing that I've done so far is some algebra. I haven't done anything, it's ugly. I did a little bit of ugly algebra, but that's all I really did was some algebra. So now what could I potentially do? Anybody see anything I might be able to do? Yeah, I could cancel things out again. So I could cancel out the tangent x plus 1s. So now I'm left with tangent of x plus 1 on the top and sine x on the bottom. So I did some more algebra. And so I'm trying to get this down into just simple trig functions. And so I'm not at that point yet. But one of the things I could do now is kind of like the opposite we did on the last problem. On the last problem, we put two fractions together. Here I have one fraction, but on the top I have two pieces, and on the bottom I only have one. So I could actually split this into two fractions. So I could split this into tangent x over sine x plus 1 over sine x. And again, all I've done is some algebra. And then a helpful trick sometimes is to think of when you have a fraction like tangent x over sine x, this is really the same as the top tangent x times 1 over sine x plus 1 over sine x. So again, all I've done is some algebra. Sure, you're talking about from this step here where I have tangent x plus 1 over sine x to here. Okay, anytime that you have only one thing on the bottom of a fraction, right? So think about it if you were going back kind of the opposite way. If I have common denominators, all I have to do is add the tops together, right? The bottom, when I do the addition, the bottom stays the same. So if you go from this step to this step, right, if I go in reverse, the bottoms are the same, so the bottom would just be sine x, and the top would be tangent x plus 1. So anytime you have only one thing on the bottom, so one term on the bottom, so in this case a sine of x, and you have multiple pieces on the top, things added or subtracted together, you can split that into two fractions with the same denominator. No problem. Other questions? Okay, so now I'm finally at a point where I can solve, or kind of not solve, but I can finally use one of those identities. So tangent is sine of x over cosine x. So I have sine x times over cosine x times 1 over sine x plus 1 over sine x. So I use the quotient identity. And now what will happen is those sine x's in that first piece will cancel each other out, right? So this sine x cancels out this sine x. So the first piece I have 1 over the cosine of x. Second, I have 1 over sine x. Again, I've just used some algebra. But now finally I'm at a point where I can make this look a little nicer. 1 over cosine x is just secant x. And 1 over sine x is cosecant of x. And these are the reciprocal identities. So we're just left with secant x plus cosecant x. Questions? No. Okay. So what we're going to do the rest of class is we are going to do what's called verifying an identity or proving an identity. So, verify the following identities. Sometimes that's called proving the identities. Proving an identity. So the first one here is I want to prove that 1 minus the cosine squared of x times the cotangent of x, that's actually the same as sine x times cosine x. Oops. I wrote and it did not show up. Oh, there we go. Super slow. Let me stop sharing and reshare here so that what I'm saying is matching up with what I'm writing. Once in a blue moon that happens in some of my classes. Okay. So we want to verify that the left-hand side gives us the right-hand side here. I generally you could start on either side. So basically we're going to start on one side and we're going to kind of do what we were doing before, simplifying stuff to show that the answer when we simplify is equal to the right-hand side. So in some ways, I actually think these are easier than the simplifying problems because you know what your final answer should be. You know what you're trying to get to. And I almost always start with the more complicated side. Now, sometimes when you get these problems, you might go, Dr. Gorman, they both seem complicated. Yeah, and then it doesn't matter which side you start with. But in this case, this side here is definitely more complicated than this side. So I'm going to start with the left-hand side, and basically we're going to do algebra. We're going to use algebra steps. We're going to use the quotient identities, the reciprocal identities, and or the Pythagorean identities to get from this side here to this side here. So if I start with the left-hand side here, probably the easiest thing to do would be to take this cotangent of x and distribute it to both of these two pieces, right? It's sitting outside of the parentheses, so I just need to multiply it times the stuff that's inside the parentheses. So the cotangent of x times 1 is just going to be, or the cotangent of x times 1 is just going to be the cotangent of x, right? So, oh, wait a minute. That's probably not what I want to do. I mean, that's fine. It's a fine thing to do. So, you could get there that way. I should be more careful. I should look at my notes to see the quickest way to get there. I should say these problems, there's the roundabout way to get the answer done, and then there's the quick way. So the roundabout way would be what I was about to do, distribute the cotangent. The quote-unquote quicker way to get there. So if you remember, the Pythagorean identity said that sine squared x plus cosine squared x equals 1. So I could subtract a cosine squared x from both sides. And if I do that, I would have sine squared x equals 1 minus cosine squared x. And if you notice, I happen to have exactly 1 minus cosine squared x, right? So I could replace the 1 minus cosine squared x with the sine squared x. So I'm going to start with the left-hand side, which we said was 1 minus cosine squared x cotangent of x. And the first thing that I'm going to do is I'm going to replace this 1 minus cosine squared x with sine squared x. So this is equal to sine squared x times cotangent x. And so all I did was use the Pythagorean identity. Questions about what I just did? No. Okay. So remember where I'm headed. Like, I kind of like to think of these as, like, this answer here is kind of like, it's like a GPS, right? So, like, or your, map app, right? So, like, if you open your phone and you're trying to get someplace, you put in your final address. So this is like the final address we're trying to get to. So we're trying to get to 1 sine x times 1 cosine x. And I'm kind of like halfway there right now, right? It's that I have 2 sine x's and I have this cotangent, but I at least have the sine x part in there. So I probably want to do something with the cotangent. So anybody have any guesses what I could maybe do with the cotangent? Yeah, so I could replace the cotangent with cosine of x over sine of x. So this is going to be, oh, and I wrote this wrong. I'm like, what? We're never going to get to cosine. And today's just, I can't copy things correct out of my notes here. So this is going to be the same as, oh no, I was right. Okay. I'm just looking at the wrong thing. Okay, so cotangent is cosine x over sine x. And that's from the quotient identity. I'm usually on my game more than this today, right? So. Okay, so I rewrote it using the quotient identity. Any thoughts on what maybe I could do right this second now?
Are you going to factor out sine squared of x?
Not that I'm going to factor out sine squared of x, but I'm going to cancel out a sine of x. So if you think about it, here, this is saying I have 2 of them, right? It's sine x times sine x. So I have 2 sine x's on the top, and I have 1 sine x on the bottom. So this sine x on the bottom would cancel out the squared part. Just like if I happen to have, like, a y squared on the top and then an x over y on the bottom, right? The y here would cancel out the square. It's the same type of deal. Does that make sense?
Yeah.
Awesome. Okay, so now I'm left with 1 sine x and 1 cosine x, which is exactly what I wanted, right? So when you're proving an identity, your answer, right? Like, I know we're used to an answer you can just box, like here's the final answer to a problem. Proving the identity is all, whoops, I didn't realize I still had the pencil going. I thought I hit point. Is all of this. All of this stuff here is your answer. You need the whole, well, that's fine, I'll draw it. You need this whole entire part is your answer. So you need all of those pieces. Questions? Okay, let's try another one. Okay, B. 1 minus sine squared x times the cosecant of x is equal to the cosine of x times the cotangent of x. Okay, so again, this one's kind of similar. Again, I'm going to use that Pythagorean identity. So remember we had that the sine squared x plus cosine squared x equals 1. This time I have 1 minus sine squared x. So if I subtracted a sine squared x from both sides, right, I would have that the cosine squared x is 1 minus sine squared x. Oops. Okay, so again, we're starting with the left-hand side, which is kind of the more ugly side. We're going to work our way to the right-hand side. So 1 minus sine squared x times cosecant x. So 1 minus sine squared x is cosine x. So cosine squared x times the cosecant of x. Equals, and that was from the Pythagorean identity. And then I could replace, my final answer, if you look where I'm trying to get to, the final place I'm trying to get to is this cosine x times cotangent x. It doesn't have a cosecant in it, so I could replace what the cosecant is. So this is also going to be cosine squared x. Cosecant is 1 over sine x. So that's because of the reciprocal identity. And then, again, where I'm trying to get to is I'm trying to get to cosine x times cotangent of x. So if you think about it, cotangent of x is cosine over sine. So what I could do is I could rewrite this a little bit. So I could rewrite, so remember cosine of x is really saying cosine x times cosine x times 1 over sine x. So I haven't used any identities. All I've done here is a little bit of algebra. In breaking up, rather than writing it as cosine squared, I could write it as cosine times cosine. And the reason that's helpful is because this first cosine here matches up with my cosine I need here, right? So I already have one piece taken care of. And then hopefully the other two pieces together can make up a cotangent. And they can, if you think of this cosine as cosine x over 1, if I were to multiply these two pieces together, I have cosine x times cosine x on the top and sine x on the bottom. So again, all I did was some algebra, right? And I'm using those square brackets just to kind of show you what I'm doing. You don't even necessarily need the brackets, but you could put parentheses. And now cosine x over sine x, that actually is cotangent of x. So this is the cosine of x times the cotangent of x. And again, I use those quotient identities this time. Questions? Okay, so cosine x times cosine x. So somebody asked me, isn't cosine x times cosine x cosine of x squared? Okay, so we got to be a little bit careful about when we're dealing with writing that squared notation. So let's take a second here to talk about this, okay? So when I have cosine squared of x, right, that means the quantity cosine x squared. But what cosine x quantity squared means that means cosine x times cosine x. When you square something, it means you're taking whatever it is and you're multiplying it times itself. So this is the same as cosine x times cosine x. Right? And so that's what I did there. I rewrote cosine, rather than use this part, I use this part, right? That cosine squared x is the same as cosine x times cosine x. The thing you want to be really careful about as you're doing these problems, this cosine squared x, that is not the same as cosine x squared. If you see this written, the only thing that's being squared here is the x. So this is like saying that the cosine of x squared. So we want to be a little careful. Those two things are not the same. So cosine squared x is the same as the quantity cosine x squared, but the quantity cosine x squared is the same as cosine x times cosine x. Does that make sense? No problem. Other questions? No. So it's just another problem where you're trying to start on one side, get to the other side. So I have another one for us to look at. So C, 1 over 1 minus the cosecant of x minus 1 over 1 plus the cosecant of x equals minus 2 tangent x secant x. Okay. So, again, I'm starting with the left-hand side. I want the left-hand side to turn into the right-hand side. The left-hand side happens to have two fractions, and the right-hand side has no fractions. So probably a good place to start would be to put the two fractions together. And we already talked about how to put two fractions together, you have to have a common denominator. And so the common denominator here, I have two different things, right? I have 1 minus cosecant x, and I have 1 plus cosecant x. So the common denominator is going to be those two things multiplied together. So if I start with 1 over 1 minus cosecant x minus 1 over 1 plus cosecant x, that's going to be the same as, I want to turn it so that the bottom, I have 1 minus cosecant x times 1 plus cosecant x minus, again, this bottom, 1 minus cosecant x times 1 plus cosecant x. Right? So that's going to be my common denominator. If we look at my first fraction, so I had a 1 minus cosecant x, and so I have that down here. And so the thing that I'm missing is the 1 plus cosecant x. So that's what I had to multiply the top by. So the top is going to be 1 times 1 plus cosecant x. And in my second fraction, the piece I was missing was the 1 minus cosecant x. So it's going to be minus 1 times 1 minus cosecant x. So if I put them together, and all I did here was some algebra. Right. So the bottom is going to be 1 minus cosecant x times 1 plus cosecant x. The top part, I have 1 times 1 plus cosecant x. So that first piece is just going to be 1 plus cosecant x minus the second piece, I have 1 times 1 minus cosecant x. So the second piece is just going to be 1 minus the cosecant of x. So, questions so far about anything I did there? So again, all I've done, again, is some algebra. No? Okay. I could take this negative and it's got to get distributed to both of these pieces. So if I do that, on the top, I have 1 plus the cosecant of x minus 1 plus the cosecant of x on the top. And on the bottom, I could actually do out that multiplication, right? So down here on the bottom, I would need to FOIL these. So I'm going to need to do 1 times 1, right? 1 times cosecant of x. We're going to have to do minus cosecant of x times cosecant of x and minus cosecant of x times 1. So on the bottom, 1 times 1 is 1. 1 times cosecant of x is cosecant of x. Minus cosecant of x times 1 is minus cosecant of x. And minus cosecant x times cosecant of x is minus cosecant squared x. So I basically FOILed the bottom and I distributed the negative on the top. So again, I've only done just more algebra. Questions on anything I did there? Okay, so now some things cancel out, right? On the top, the things that cancel out are the 1 and the minus 1, right? They go away. And I have 1 cosecant of x plus another cosecant of x. So on the top, I'm left with 2 cosecants of x. And on the bottom, I have a positive cosecant of x, and that's going to cancel out with the minus cosecant of x. And so on the bottom, I'm left with 1 minus the cosecant squared of x. And again, all I've done is some algebra. So you might go, it doesn't really look like we're getting to where we need to go. And I'm going to tell you, that's not true. We are getting to where we need to go. First off, we have the 2, right? So if you notice, my final answer here has a minus 2 tangent x secant x. And so there was a 2, and I now finally have a 2 in my problem, right? So before my problem didn't have a 2 in it, now it does. So we are getting there. 1 minus cosecant squared x, that's a good candidate for using a Pythagorean identity. So if you go back to where we did the Pythagorean identities, one of the Pythagorean identities that we had was that the cotangent squared of x plus 1 equals the cosecant squared of x. So I can replace cosecant squared of x with cotangent of x plus 1. So this is going to be 2 cosecant x over 1 minus, so instead of cosecant squared x, we can put cotangent squared x plus 1. And that, we've used the Pythagorean identity. And let me move this up here a little bit. So now I could distribute that negative in the bottom. So I've got 2 cosecant x on top divided by 1 minus cotangent squared x minus 1 on the bottom. That's just some algebra. And again, my 1 and my minus 1 would cancel. And so right now we're at 2 cosecant x over minus cotangent squared x. So again, all I've done is algebra. Again, the thing you want to remember is where we're trying to get to, right? So the thing that we are trying to get to is minus 2 tangent x secant x. So the thing to remember is these problems are sometimes a little bit long, right? So I'm trying to get to, so if I pull this up here, I'm trying to get to minus 2. We'll make a little, reminder for ourselves. So our goal is to get to minus 2 tangent x secant x. So I have the 2, and now I have the minus. So all I have left to do is somehow get cosecant of x, cotangent squared of x into tangent x secant x. One of the things that I could do is I could rewrite this again a little bit nicer. So I could write this as minus 2 times 1 over cotangent squared x times cosecant x. So I've kind of just rearranged terms a little bit. So again, this is just some algebra steps. There's usually a lot of algebra steps. But the reason this is helpful is because 1 over cotangent, we talked about with the reciprocal identities, is actually just tangent. So this is minus 2 tangent squared x cosecant x. And that's from the reciprocal identity. So we're almost there, I promise. Remember, my final answer just has 1 tangent in it, and right now I have 2 of them. So just like we did in the last problem where we broke it up, we're going to do that same thing now. So this is going to be minus 2 tangent x cosecant x. And again, that's just some algebra. So I'm not looking too bad, right? I have a minus 2 and a tangent x so far. So this minus 2 part, this tangent x part, those are good and I need them. And so I just have to worry about somehow, hopefully, this tangent x turns into a secant. And so I'm going to basically rewrite. Oh, it's not going to let me. All right, we're going to have to copy this last line here. And let me go to another page. Okay. So this is what we have. Remember, we're trying to get to minus 2 tangent x secant x. And since it wouldn't let me write any further down. So I'm going to rewrite tangent x and cosecant x using identities. So this is going to be minus 2 tangent x. Tangent x is the same as sine x over cosine x. And cosecant x is 1 over sine x. So I basically use the quotient and reciprocal identities. And this is nice because the signs would cancel. So we're left with minus 2 tangent x times 1 over cosine x. And again, all we did there was some algebra. And then finally, 1 over cosine x is secant of x. So finally we get to what we were trying to get to. So minus 2 tangent x times the secant of x. And that is using, again, a reciprocal identity. So some mathematicians love these proving identity problems, right? I don't. So I think it's kind of, I mean, it's fine, but they're long. It's like you just kind of have to like chug through them and figure out the correct way to get there. There's only a couple problems on Alex that you have to do that have to do with the identities. More of the problems in Alex, they like give the step and you have to say what happens. And when I've put problems like this on a test, that's how I've done it. I've like written out all the steps and said, what did I do in each step? Like tell me what I did in each of these steps. So that's probably how I would do it on the next test. I am much more into, let's just use the identities. Let's use them to help us out doing things rather than actually just stay proving stuff. So some mathematicians, they love proving all this identity things. That's not me. We are not going to spend a long time proving identities. It was today. We're done. We're not going to prove after this. And I think I have like maybe like one topic in your homework that is proving identities. So you might, you're going to have to do a couple of them just to kind of like give it a try. But after that, you're not going to need to do these. Questions? No? Okay, so then that's it for today. Next class, we're going to actually look at all the rest of the identities, and we're going to look at how to actually use them. So the more interesting part. Yeah, no, there won't be a problem this hard on the test. Nope. Yeah, it's just not worth it. There's much more important stuff we're going to do than proving identities. All right. Well, you guys enjoy the rest of your day. Thanks. You too.